Good afternoon, everyone. Thank you for coming. The title of my talk is Magic Lenses for RHIC, Compensating Beam-beam Interactions. The magic lens I mean is the electron lenses, RHIC. You may know the relativistic heavy ion collider. The beam-beam interaction is the interactions between particles or from two colliding bunches. In this talk, I first will explain to you why do we need electron lenses. And then I will discuss with you the details of RHIC electron lenses, followed by conclusion. In the first part, why do we need electron lenses? I will start with the collider, RHIC, and luminosity. Then we'll discuss with you, introduce you beam-beam interaction and beam-beam compensation. First, we are made out of matters. What is matter? Matter is everything around us. Matter has mass and volume. Solid, liquid, gas, and plasma are all matters. The basic units of matter is atoms or molecules. The molecules are also made of atoms. The size of atom is about 10 to minus 10 meter, which is 5 orders smaller than the of magnitude smaller than the diameter of human hair. In the center of atom is the nucleus with size 10 to minus 14. Outside of the nucleus is a cloud of electrons. The electrons are negative charged. Electrons spin around the nucleus. The force between the electrons and the nucleus is electromagnetic field. Nucleus consists of protons and neutrons. Both protons and neutrons are made of quarks. For example, one proton is made of one down quark and 2 upper quarks. The force to bind those quarks together in so tiny space are strong force. The gluon particles are the exchange particles of the strong force. So far, we don't know the inner structure of quark yet. And even for known particles, we still don't completely understand their properties. Why do we need colliders? To study particles, we collide particles. To collide particles, to break the particles, to study the inner structure of them. There are 2 ways to collide particles: fixed target experiment and using colliders. Here I discuss with you the efficient condition energy from those 2 experiments. First, we say we discuss 2 particles collide head-on. Those 2 particles are exactly same, only different with their energies. In the fixed target experiment, a particle with high energy E hit the fixed target and collide head-on with one particle inside of the fixed target. The particle in the fixed target is at rest. Its energy is mc squared. M is the mass of the particle. C is the speed of light. For this kind of condition, the total energy in the center of mass is given by square root of 2e mc squared. Then we move to the collider. In the collider, we collide 2 particles head-on. Both particles with high energies E. The total energies in the center of mass is given by 2e. Normally, they consider the high energy particles energy E is much larger than the particle's energy at the still particle's energy, mc squared. So the total energy in the center of mass from the collision in the collider is much higher than the center from from the fixed target experiment. So that means a collider can reach much higher energies. Much higher energies means we can provide more violent conditions and more efficient conditions with a better chance to discover the inner structure of particles. As you know, Brookhaven National Laboratory is the home to the relativistic heavy ion collider, or RHIC. RHIC is a double-ring superconducting collider. The circumference of RHIC is 2.4 miles, and the diameter is 3/4 of 1 mile. RHIC is the only running collider in the United States. RHIC collides heavy ions and polarized protons. RHIC is one of the two existing heavy ion colliders in the world. The other one is the Large Hadron Collider, RHIC, at the European Nuclear Research Facility, CERN. RHIC is the only high-energy polarized proton collider ever built. By colliding heavy ions, we generated high-temperature quark gluons. Quark gluon plasma existed in the very beginning of our universe, less than 10 to minus 21 seconds after the Big Bang. The temperature of the quark gluon is about 4 trillion degrees Celsius, which is about 250,000,000 hotter than the center of the sun. By colliding the polarized protons, we are going to solve the mysteries of proton spin crisis. As you know, the proton is made of 3 quarks. However, experiments from other laboratories and from RHIC shows the quarks only contributed about 20% of the proton spin. So we are finding the rest of the source of the proton spin. Today, I only focus on the proton collisions in RHIC. RHIC is capable of collision and polarized protons with energy up to 250 GeV. What does that mean? Normally, we use EV or electron volt to measure the particle's energy. 1 EV is the energy gained by 1 particle, 1 electron or 1 proton accelerated by 1 volt. You know for the normally AA or AAA batteries, the voltage is 1.5 volt. 1 GeV or 1 gig of EV is 10 to 9 EV. To reach the 250 GeV energy, we need 250 times 10 to 9 volts to get that energy. So particles after protons are generated from the source, they are continuously accelerated in the linear accelerator, in the booster, in the edges, and also in the RHIC. Next, I explain to you how do proton particles collide in the ring, in the RHIC. RHIC consists of 2 rings. We name it the blue ring and the yellow ring. This picture is taken in the RHIC tunnel. Here you can see 2 rings lie side by side. Those 2 rings intersect each other at 6 symmetry positions around the circumference. We name those intersection points as IP6 at 6 o'clock, IP8 at 8 o'clock, and so on, IP10, 12, and IP2, and IP4. The particles in the blue ring circulates in the clockwise, and the particles in the yellow ring circulate counterclockwise. The particles from different rings collide at IP6, where the star detector is and at IP8, where Phoenix detector is. And the detectors are used to detect what happens when 2 protons collide. Actually, the particles traverse in the ring in groups. Each group we name is a bunch. In RHIC, each ring have 109 proton bunches. Each bunch holds more than 10 to 11 protons. Here I show one bunch. Of course, not in the actual sizes. In each bunch, there are more particles in the bunch center, and less and fewer particles in the bunch tail. In the tail, the particle distribution in one bunch is Gaussian in 3 dimensions: in the longitudinal direction, and the vertical direction, and the horizontal direction. At the 250 GeV, the 4 weights of the proton bunch length is about 3.5 meters, and the height or the weight of the one proton bunch is in the order of 1 millimeter. At the collision point, IP6 and IP8, the weight is about 0.5 millimeter. So when 2 bunches collide each other, each one with more than 10 to 11 particles. However, there are only few particles, only several particles actually, really can hit the particles from the other proton bunch. The rest of particles will go through the rest of the opposite bunch and continue circulating in the ring. Here we define one happening that one proton hit another proton is one event. Here I show the illustration of the one event sent by the star detector and one event sent by the Felix detector. To study the particle collision, we need a large number of events, huge number of events, to reduce the statistical error in this study. So to accumulate such a huge number of events, we require a high event rate. Event rate is defined as the number of events generated per second. Event rate is proportional to the luminosity. Luminosity is the collision rate per unit cross section. This is the only decided by the collider parameters and the proton bunch parameters. Here I will go through with you the luminosity equation. Luminosity is represented here by L. Luminosity is proportional to the revolution frequency. The revolution frequency is how many turns one particle go around the ring, the collider. For RHIC, the particles will go 78,000 turns in 1 second. Luminosity is also proportional to the number of bunch collision per turn. Each turn, the particle finishes one turn in 12.8 microns. In such a short period, there are 107 pairs of protons collide at Phoenix, and 102 pairs of protons bunches collide at the star. Luminosity is also proportional to the square of bunch intensity. The bunch intensity is how many particles, the populations in one bunch. For RHIC is in the order of 10 to 11. And the luminosity is also inversely proportional to the transfer to the bunch cross section, which is given by 4 pi sigma square. Here I assume the bunch is Gaussian distribution. The sigma is given by this equation. For existing colliders, the revolution frequency and the number of bunch collision per turn are fixed. To increase the luminosity, we would like to increase the bunch intensity and reduce the bunch size, sigma. Here I go over with you the luminosity progress in RHIC proton operation. RHIC became operational since the year 2000, and we delivered the first proton collision for physics with proton energy 100 GeV in 2002. And In 2009, we first delivered the proton collision with proton energy 250. Here I show the peak luminosity in the past decades. Around the years, vertical is the peak luminosity in unit of 10 to 30 inverse centimeter square and inverse second. The pink curve shows the peak luminosity from the 100 GeV condition, and the red curve shows the peak luminosity from the 250 GeV condition. In the past 2013 proton operation, we achieved a peak luminosity in RHIC is 2.38 10 to 32. The increase in the luminosity is accompanied with the proton bunch intensity. In the beginning of the RHIC proton operation, in 2002 to 2004, the maximum proton bunch intensity increase is about 75 10 to 11. In 2013, we collided the maximum proton bunch intensity is reaching 1.85 10 to 11. For the next RHIC luminosity increase, we are going to increase the luminosity with a new proton source. With this new proton source, the bunch intensity in RHIC is expected to reach 3 10 to 11. And the peak luminosity is expected to be doubled from current one to almost 5 times to 32. To reach this luminosity goal, besides a new proton source, we still need a piece to bridge the gap between current luminosity and the luminosity goal. This piece is electron lenses. We are going to use electron lenses to compensate the beam-beam interactions. Beam-beam interactions between particles from two colliding bunches. Because the beam-beam interactions prevent the luminosity increase even with the high bunch intensity. Before I talk about the electron lenses, I would like to introduce you some accelerator basics. Accelerator is a machine to accelerate particles to high energies. Colliders are accelerators, and the synchrotron radiation net sources are also accelerators. Accelerator consists of dipole, quadrupole magnets, and the radio frequency cavity, and other magnets and beam components. Here I show a schematic diagram of dipole magnets. Each dipole magnet consists of two magnetic poles, north pole and south pole. We use this kind of dipole magnets to bend the particles around the collider. Here shows a schematic diagram of quadrupole magnets. Each quadrupole magnet consists of 4 magnetic poles, 2 north pole and 2 south poles. We use quadrupoles to focus the particles transversely to achieve a small transverse bunch size. This picture shows the radio frequency cavities used in RHIC. We use radio frequency cavities to accelerate particles and to feed the particles' energy and to focus the particles' longitudinal direction to achieve a short bunch length. Particle motion. Particle travels around the beam pipe at almost the speed of light. At the same time, particle oscillates in the transverse plane. What does this mean? It means the particles not always stay at the design orbit or the reference orbit. It sometimes is above, sometimes below, sometimes outside, sometimes inside of the reference orbit. Here I show the horizontal position of particles in one proton in 2 turns. The red curve shows the position in the first turn, and the blue curve shows the horizontal position in the second turn. To be clear here, I pick out the first turn's position, horizontal position and unfolded here. The horizontal axis is the position around the ring. It's the one turn is 20 to 2.4 miles, and the vertical axis is the horizontal position. Positive value means outside is the reference orbit. Negative value means inside the reference orbit. The oscillation amplitude is about a millimeter. To measure how fast the oscillation is, or the frequency of the particle transverse oscillation, I introduce you an important concept, tune. The tune is the number of oscillations the particle performs in one turn. For example, for the RHIC proton tunes, per protons, in one turn, the proton oscillate performed horizontally 28.695 oscillations. So the horizontal tune is 28.695. So the vertical tune is for RHIC proton is 29.685. You can say the tunes have two parts: is integer part, integer tune, and the fractional fractional tune. For a stable particle motion, the tune of the particles can be only have integer part, and even the fractional part tune can be some rational numbers. The reason is resonance. To understand resonance, first we take a look at the swing. The case under the swing form a system. It has its own frequency, move back and forth. If the parents push the case with this frequency, or push coherently or resonantly, so the parents can push the case higher and higher. So this phenomenon is resonance. However, the parents have to stop at some point. Otherwise, they will push the case too high, and the case will fall off the swing. In collider, we also have resonances. The resonances drive particles to large amplitude, and the particle will have bunch size increase and also maybe have particle loss. To keep particles motion stable, resonance should be avoided. Here I give the transverse resonance condition. MQX plus NQY equal P. QX and QY are the horizontal tune and QY is the vertical tune. M and P are integers. M plus N is the order of resonance. To show the resonance, we'd better to draw resonance in a two-dimension diagram space. We call this is a tune space. Here I show the horizontal axis is the horizontal fractional tune, and the vertical axis is the vertical fractional tune. Here I dropped the integer part. However, keep in mind, for stable particle motion, the tune can only have integer part. Here, each red line is one represents one resonance. Here, I draw resonance up to 10th order. Normally, the lower order of resonance are more harmful to the particle motion, and the higher order of resonance is less harmful to the particle motion. The RHIC proton tunes are in this blue corner. So we zoom into this corner and put the tune of the RHIC proton tune inside. In this tune space, there are two important resonances. One is the third order resonances, which happens when the horizontal tune equal 2/3, or the vertical tune equal 2/3. Another important resonance here is 10th order resonance line, which happens when the horizontal tune or the vertical tune equals 7/10. The 10th order resonance line is also a spin resonance line. When the particles stay close those two lines, the proton's polarization will get lost. So for the proton operation, normally we keep the tunes away from those 10th order resonance line. Knowing the tune and the resonance and the tune space, we are at the right place to take a look at the beam interaction. As I said, when two proton bunches collide each other, each with more than 10 to 11 protons, only a few protons really can hit protons from the opposite bunches. Most of the particles will only go through the opposite bunches. Here I give an example. We take one particle from the left bunch, and we check how its motion is affected when it goes through the right bunches. Because the proton is positive charged, and this proton bunch is also positive with more than 10 to 11 protons. When this proton passes by the opposite proton bunches, the electromagnetic force from the proton bunch is pointing outwards. So the proton particle will be repelled away from the center of the opposite bunch. The force is called beam force. Here I show the beam force with respect to the distance of the particle to the center of opposite bunch center. So here you can say the beam force is nonlinear. It strongly depends on the distance between the particle and the center of the opposite bunch. The beam force is quite different from the force given by the common magnets. The force from the magnets normally increases continuously with the distance of the particle and between the distance between the particle and the center of the magnet. The beam force is defocusing. It slows down the particle oscillation and reduces the proton tunes. So here I put back the tune diagram with the bunch intensity 1.5 to 11. Without the condition, the tune I put here is 695 horizontal tune, vertical tune is 685. So with the beam interaction, the particles tune will be reduced, go this direction, so move towards the third order resonance line. However, consider the beam force is nonlinear. So each particles in this bunch with a different position will see different force from this opposite bunch, and will have the different tune shift. For example, one particle in the center of this bunch, when it goes through this opposite bunch, so this tune will move from here to here, very close to the third resonance line. And if we draw the tunes of every particles in this bunch, it will generate a spread. We call this spread as beam tune spread. Unfortunately, the size of beam tune spread is proportional to the proton bunch intensity. If the proton bunch intensity is big, so the tune spread will be big. Here I show the beam tune spread with proton bunch intensity 2.5 10 to 11. Here you can say the tune spread with beam interaction is too big to fit in the resonance-free area. Some particles tune already pass or cross or on the third order resonance line. Actually, in the current the tune space between 2/3 and 7/10, this area, there is not enough tune space to hold the beam tune spread when the proton bunch intensity is bigger than 2 10 to 11. So what will happen when the proton bunch intensity is bigger than 2 × 10⁻11? The beam-beam interaction will push the tunes of protons to the third-order resonance line. And the third-order resonance line will blow up the particles oscillation amplitude to generate, so that causes the large bunch size and cause particle losses. From this equation, particle loss and the sigma, the beam size increase, both reduce the luminosity. Actually, in the 2013, in the RHIC proton operation, we already hit the wall. On one side, to increase the luminosity, we were very eager to increase the proton bunch intensity. However, with the bigger bunch intensity, the beam-beam interactions reduce the luminosity. So in the 2013 RHIC proton operation, as a compromise, we have to reduce the proton bunch intensity in the normal operation. Since the beam-beam reduces the luminosity, is there a way to compensate the beam-beam interaction? The answer is yes. So let we first check the beam-beam interaction. It's two proton bunch collide each other, and one particle from one bunch 1, goes through the proton bunch 2 and get repelled away from the bunch center, the center orbit. The proton bunch 2 actually acts like a defocusing lens. So the idea for the beam-beam compensation is to introduce a low-energy electron beam at other location in the ring to let the proton bunch 1 to go through head-on collide the electron beam. And for the same particle, when this particle goes through the electron beam or bunch, the proton bunch, this will be focused, and the electron beam actually acts like a focusing lens. The device to provide such an electron beam is called an electron lens. To choose a low-energy electron beam is to reduce the cost to build this, to provide the electron beam. This is log of is RHIC E lens. Here we use DC electron beams. We guide them into the beam pipe and go through the interaction part, and after that, guide them out. It's DC beam. And the proton bunches goes from the left to the right and goes through the electron beam. And the interaction is covered with superconducting solenoid. Beam-beam compensation is very complicated. Here I discuss with you the conditions of beam-beam compensation. For simplicity, here I only discuss a very simple case with one proton, one beam-beam interaction, proton bunch collided with proton bunch, and one electron lens. To perfect compensate the beam-beam interaction with this E lens to compensate the beam-beam interaction, we have to meet the following conditions. First, the electron beam should have the same transverse profile as the proton bunch, which means the electron particle distribution should have the same distribution as the proton bunch at the E lens. And also the size of the Gaussian distribution of the electron beam also should be the same as the proton bunch's transverse beam size. Secondly, the electron beam should have the same particle numbers as the proton bunches. The third, the phase response between the beam-beam interaction and the E lens should be k pi. K is an integer. This means the oscillation between the beam-beam interaction and the E lens, the particle oscillate multiple the multiples of half of oscillation. Half oscillation is the phase response of half oscillation is pi. So next, I move to the second part of my talk. I will discuss with you the physical design and parameter tolerance of RHIC electron length, and also introduce you project status and outlook. To compensate the beam interaction in the RHIC, we need two electron lengths, one for the blue ring, one for the yellow ring. I remind you there are two proton beam interactions at IP6 and IP8. We place the electron lengths at IP around IP10. So zooming in here, we put the blue ring electron length on the south of the IP10 and the yellow electron length on the north of the IP10. So for the proton bunches from the blue ring, we're going from south to the north. First go to the blue ring electron lengths and go to yellow ring electron lengths and then bend into its own ring. For the bunches from the yellow ring, was first method they go through the yellow ring electron lengths and then go to the blue ring electron lengths, then back to its own ring. There are 4 beams, 2 proton beams and 2 electron beams. How do we accommodate those 4 beams in the same beam pipe? First, let's look at from the top. We guide the electron beams horizontally inside the beam pipe. The proton bunches from the blue ring only interact with the electron beam from the blue ring electron length. The same, the protons from the yellow ring only interact with the electron beam from the yellow ring electron length. To avoid the collisions of the proton bunches from 2 different rings, so we separate them vertically. So from this here, the side view, the proton bunch from the blue ring and the electron beam from the blue ring electron length are placed 10 millimeters above the proton bunches from the yellow ring and the electron beam from the yellow electron length, yellow ring. So here I list the beam electron particle parameters. The energy is 5 keV. It's low energy, and the current is maximum is 1.2 ampere. 1.2 ampere is enough. Will provide 3.5 10 to 11 electrons in the interaction range. And the transverse beam size of the electron should be the same as the proton bunches at the E-length. So for the 100 GeV beam compensation, the transverse beam size of the electron beam from the E-length should be 800 micron. And for the 2-phase GeV beam compensation, it will be 300 microns. The effective interaction length is 2.1 meter. Here I show the electron length system. We have two electron lengths. So here I only shows one of them. For example, the blue ring electron lengths. Each electron length system includes electron gun and transfer line on the gun side, which consists of 3 magnets, superconducting solenoid, and the transfer line on the collector side. This one is the electron collector. The electrons generated from the electron gun and go through the gun side transfer line and are guided into the superconducting solenoid and then guide out and dumped at the electron collector. The proton bunches comes from the right to the left. It go inside the superconducting solenoid and in the superconducting solenoid, it goes through the electron beam. So here I show you how the tune spread change with the beam in compensation with the electron lenses. In RHIC, we have two conditions, one at IP6, one at IP8. Each ring we only have one electron lenses. In RHIC, we adopt partial beam compensation. For example, with half beam compensation, we use the inners at IP10 to compensate the beam interaction at IP8. So here's this one already showed the beam tune spread without the beam compensation with the proton bunch intensity 2.5 10 to 11. So it's already touches cross the third order resonance line. Here, with the half beam compensation, the tune spread, beam tune spread is reduced by almost half. So the tune spread with the compensation is reduced and just can be fitted in the resonance free range area. Here I explain you why do we need a superconducting solenoid. Because we use low energy electrons. Low energy electrons are strongly disturbed by the proton bunches to stabilize the electron motion in the interaction region. So we use a strong 5 Tesla solenoid. The solenoid is given by like this. So it generates a uniform magnetic field, partly the electron's motion. Here I show my simulations to prove that, to convince you that the importance of the superconducting solenoid. Here I simulate one proton bunches go through the electron beam. So we pick out one slice of the electron from the electron beam and check how the electron beam size change. For perfect beam compensation, we need the size of the electron should be constant. For example, at 250 GeV should be stay 300 microns the beam size. Here shows the simulation results. Horizontal axis is the time, vertical is the electron beam size. This will take about 14 nanoseconds for the proton bunch to pass by this electron slice. The vertical axis shows the size change of the electron slice. Here I show the different with the results with different magnetic field of solenoid, 0.1 Tesla, 0.2 and 0.5 Tesla, and 5 Tesla. So from here you can say the bunch, the electron beam size are reduced with when the proton bunch pass by with a low magnetic field. With the 5 Tesla, however, the electron beam size keep almost constant of around 300 micron. So that's why we use superconducting solenoid. Next, I will discuss use the parameter tolerance for the beam compensation. First, we discuss the electron transverse profile. As you already learned, the electron beam must have the same transverse profile as the proton bunches to generate the same amplitude dependence of the force. For example, here shows the particle distribution of one proton bunch. Have more particles inside and a few particles in the tail. Its distribution is Gaussian. For the RHIC proton bunches, there are particles up to 5 to 6 sigmas. Here shows the electron beam's electron particle distribution from the electron gun of the electron length. Due to the finite size of the catheters, the electron beam's Gaussian distribution is cut off at 2.8 sigma. That means above 2.8 sigma, there is no electrons. So here I do simulation. Here I show my simulation results to to investigate the tolerance of the Gaussian tail cut of the electron beam. Here I track the proton particles in 2 million turns, which corresponds to 24 seconds. The vertical axis shows the proton particle losses. The unit is percent. So you can say the particle loss in the 24 seconds is very small. However, I have to remind you that after we brought the bunches into collision, we will keep those bunches colliding up to 7-8 hours, even more than 10 hours. So we have to reduce any unnecessary particle losses. For particle losses, 0.007% in 24 seconds, it corresponds to 1% particle loss in one hour. Back to the simulation results. With the perfect Gaussian distribution of the electron beam, the particle loss of the proton beam particles in one bunch is given by the red curve. If we compensate, we use electron beam with the Gaussian tail cut at 2 sigma, given by the black dot curve. So there have more than 50% particle loss than the perfect condition. Then I show you the proton particle losses with the Gaussian tail cut at 2.5 sigma and 3 sigma, the green one and the blue one. So compared with the perfect situation, the particle loss of proton particle loss is almost comparable with the perfect condition. So we conclude that the electron bunch Gaussian tail cut at 2.0 sigma is acceptable. So that means the design of the electron gun for the RHIC electron lenses is acceptable. Another important issue is to overlap the electron and the proton beam. Accurate overlapping electron and the proton beams is crucial to the success of the beam-beam compensation with electron lenses in RHIC. Here I show the perfect overlapping of the proton bunch and the electron beam, center by center. Here I show the overlapping with some transverse offset. They shifted. So the electron, there are some transverse offset delta between the center of the transverse offset between the center of the electron bunch and the electron beam. Here I show the force from the electron beam. Horizontal axis is the distance of the one proton particle to the center of a proton particle. So the red line shows with perfect overlapping, and the blue curve shows with offset errors. So from here you can say with the same x, the force is different, even though the force is only shifted in the right side. Here I do show my simulation result again to set the tolerance of the electron-proton overlapping. Here again, this vertical axis is proton particle losses in unit of percent. 0.012% loss in 24 seconds means 2% per hour proton particle loss. The red curve is the perfect overlapping. Here I show introduce the random offsets with amplitude of 3 microns, 6, 9, 12, 15 microns. So you look carefully, you can say when we increase the amplitude of the random offset from 3 to 6 to 9 to 12 and to 15, we have more and more proton particle loss. Based on this simulation, we set the tolerance of the electron and the proton center offset to be 9 micron for the random offset, which is the 9 micron is almost 1/30 of the proton bunching size. So to reach this goal, So we have the power supply of the electron of magnets should the stability of the magnet's current should be better than 10 to minus 4. And we are developing new instrumentations, new instruments to detect the tiny, to detect and to control the tiny offsets. Finally, I will show you the real parts of the RHIC electron lenses. This one is the electron gun. Is about 5 inches long length, and this one shows the electron collectors. It's about 9 inches because the electron beam dumped into the electron collectors and will deposit the energy inside the surface of the electron collector. So here we use water cooling to cool the collectors. Both were designed by Sasha Pink, experts of electron and ion sources. Here I show the transfer line magnets. For each electron lens, we have 6 magnets, and totally for 2 electron lenses, we have 12 of them. This one is the biggest one. The width is 15 inches. The superconducting solenoid was designed and manufactured in the superconducting magnet division. Here I show a picture of one solenoid during winding. Before the 2013 RHIC proton run, we installed one real RHIC electron lens into RHIC tunnel. Here I show it. This one is the superconducting solenoid. The length is about 2.8 meters, and as I said, the effective interaction range is 2.1 meter. Here is the electron gun size, the transfer line. This one is the transfer line on the collector side. Outlook. In the summer, we will continue the installation of the blue ring electron lenses, and we will install the yellow ring electron lenses in the RHIC tunnel. And currently, the experts are commissioning electron beams. That means to transfer the electron beams from the electron source, go through the superconducting solenoid and dump into the electron collector. In the next RHIC proton run, we will continue commission electron beams, and also we need to commission proton beams, and to overlap the electron beams with the proton bunches. After that, we are at a right position to investigate the beam compensation and to see the luminosity increase. Conclusions. To double the luminosity in the RHIC proton operation with high proton bunch intensities, electron lenses are needed to compensate the beam interaction. 2 electron lenses are being installed in RHIC. Commissioning of electron beams and the beam compensation are in progress. Please stay tuned. Acknowledgement. The RHIC electron project actually, same as other project, is teamwork. It's involved many people, many experts from the collider accelerator department, and also from the superconducting magnet division. Thank you for your hard work in the past over 7 years in the electron lens development. And we also have got received help from individuals from other laboratories, like Fermilab. We learned a lot from them, and from CERN. And finally, I also wanted to thank our funding agency. This work is funded by the United States Department of Energy. And finally, I wanted to thank you for coming. Thank you for your concern. Thank you.
Thank you for the very nice lecture. We have a couple of minutes for a question or two, then we will have refreshments outside. Then you can discuss the details with the speakers. Any questions?
Please.
So for a normal length lens, I can define something like a focal length. Can one say something about that?
In the accelerator, actually, we use quadrupoles to focus particles transversely to achieve small bunch size. Sometimes we also call the quadruple magnets as a lens. If this focusing is a focusing lens, if defocus is a defocusing lens, and we place the focusing magnets and interleave with the defocusing magnets, so we can achieve much smaller transverse bunch size. So for the electron, for here we use electron lenses because to the first order, the electron lens, the electron beam act like a focusing lens.
Right, but I mean, can one say it's a focal length of 100 meters,
or
1 meter, or mile?
Okay, sorry, this is what your question. So this one I didn't calculate. I can get back to you later. I never calculated I only know the focusing strength is integrated focus strength. So it's about 0.01. It's will change to 0.01 like that. Please.
Is it possible to do the compensation of the interaction point?
The question is, can we put the electron lens at the interaction point? My answer is no, because due to there we already have the detectors. It's already tight enough there. So in the beam compensation, the compensation is global compensation, is not local compensation.
One more question.
You mentioned that the phasor one between the lens and the interaction point should be, say, an integer number of pi's. RHIC has, say, two detectors, two interaction points. Do the unit phase shift between this interaction point and also, say, integer number of pi's?
Okay. So the question is, I showed for the one beam collision and one electron lenses, for the perfect compensation, the phase response between the beam interaction and the electron lens should be multiple. The phase response should be multiple of pi. So his question is that in RHIC we have two conditions at IP6 and IP8. So how do we generate such k pi phase response? As I mentioned here, in RHIC we adopt partial beam compensation. So we use the beam E-lens at IP10 to compensate the beam interaction at IP8. So we adjust the phase response between the IP8 and E-lens at IP10 to k pi, and leave the beam interaction at IP6 uncompensated. And we also from simulation shows that with 4 beam compensation, which generate even smaller beam tune spread, this will cause more proton-particle loss, because the E-lens is a nonlinear element. It's introduced more nonlinears into the ring with 4 beam compensation.
Okay, I would say close the lecture and encourage you to discuss more details with speaker outside. We have some refreshments. Thank you.
Thank you.